So think about this for a second. Right now, your phone, it's basically screaming into a digital void, just desperately begging a local router for a name.
Oh, yeah, like constantly.
Right. And if it doesn't get one in, I mean, literally a matter of milliseconds, your internet is completely dead. We don't really, think about it when we sit down at a coffee shop and tap that little Wi-Fi icon.
No, we just expect it to work.
Exactly. We just expect to open a browser and instantly start streaming or working. But what you don't see is this massive invisible handshake happening in the background. In that split second, your device is essentially showing up to a massive, crowded digital city with no identity, no address, and no map at all.
It's completely blind.
Yeah. It has to rapidly ask for all of those things before it can load even a single web page.
It really is a frantic negotiation. And understanding how that negotiation actually works is, it's pretty much the ultimate cheat code for anyone who wants to grasp modern technology.
Which is exactly our mission for this deep dive.
Right. And today we are using a stack of certification training notes from Professor Messer's CompTIA plus 220 1201 courses to act as our blueprint.
It's a great foundation.
It really is. These modules map out exactly how IP addressing works, and specifically they detail this massive architectural leap from IPv4 to IPv6 that is currently, rewiring the globe.
And by the end of this deep dive, the random numbers buried in your computer's network settings and, honestly, the incredible problem solving behind them are going to make perfect sense.
Definitely.
But looking at these notes, I don't really get why my IP address alone doesn't just immediately get me online. Like, if an IPv4 address is supposed to be my unique identifier, why do we need a bunch of other settings just to load a website?
Well, because a single number on its own kind of lacks context. Let's look at the foundational structure first. IPv4 is a 32-bit address.
Okay.
At its core, the computer just processes a string of 32 ones and zeros. But humans are terrible at reading binary.
Oh, absolutely terrible.
So to make it readable, we break those 32 bits into 4 groups of 8, which we call octets, and we convert them to decimals separated by periods.
Right, so that's why it looks like 4 separate chunks.
Exactly. And because an 8-bit binary sequence can only reach a maximum decimal value of 255, you get addresses that look like, 192.168.1131.
Ah, okay. That makes sense.
But that number just floating in a vacuum tells the device absolutely nothing about its surroundings. To actually move data across a network, your device needs what they call a holy trinity of connectivity.
Okay, let's unpack this. I see the trinity right here in the notes. We have the IP address, the subnet mask, and the default gateway.
Yep, those 3.
So if we use the classic networking analogy, imagine your network is a physical neighborhood.
Okay, I like this.
Your IP address is your specific house, say 123 Main Street. The subnet mask defines the borders of your neighborhood. It acts kind of like a property line that tells you which houses you can walk to without actually leaving your subdivision.
Right.
And then the default gateway is the local post office that handles any mail leaving your town.
That analogy holds up perfectly, honestly, because it perfectly mirrors the underlying routing logic. The subnet mask is literally, masking your IP address.
Masking it how?
It uses this mathematical operation behind the scenes to split your 32-bit IP address into 2 distinct pieces. You've got the network portion and the host portion.
So the neighborhood and the house.
Exactly. Your computer looks at the IP address of the website you want to visit, compares it against its own subnet mask, and basically asks a really simple question. Is this a destination inside my local network, or is it outside?
And if it's inside, it just talks directly to that local device, right?
Right.
Like sending a file to the computer in the next room.
Right, no post office needed. But if it's outside,
Then it immediately hands the data over to the default gateway.
you got it. And the default gateway is, it's almost always the local router's IP address on your network. Without that gateway, your device is just trapped in its local subdivision.
It can talk to the printer down the hall, but it has no exit path to the actual internet.
Exactly. And if you throw in a DNS server, which translates human-readable web addresses into IP numbers, and an NTP server to keep your system clock perfectly synchronized for, secure connections, you have the complete toolkit required for modern networking.
Which, honestly, brings up a logistical nightmare.
How so?
Well, if that's the complex toolkit required, how do those numbers actually get into the device? Because I'm certainly not typing out a subnet mask and a gateway every single time I walk into a different room with my laptop.
Oh, thankfully, no one is doing that. We rely on DHCP, which is the Dynamic Host Configuration Protocol.
DHCP. Okay.
The literal moment you connect to Wi-Fi, Your device broadcasts a request, and a DHCP server responds by leasing you an IT address, a subnet mask, and your gateway information entirely automatically.
Which is incredibly smooth for an end user.
Yeah.
But looking at the enterprise sections of the CompTIA materials here, it talks heavily about manual static IPs.
It does, yeah.
If DHCP automatically hands out these configurations so flawlessly, why would any network administrator ever want the headache of manually typing in a static IP? I mean, one typo breaks the connection entirely.
This raises an important question. Why abandon automation for manual labor?
Exactly. Why do it?
The answer basically comes down to structural predictability. Think about a massive corporate environment. You have network printers, internal file servers, heavy-duty firewalls. You absolutely cannot have the address of your main firewall changing dynamically every time the building loses power.
Oh, right, because no one would know where to find it.
Exactly. If the primary printer's IP address shifts because the DHCP server handed it a new random number from the pool, suddenly hundreds of employees can't print.
Their computers are blindly sending documents to an old address that just no longer belongs to that printer.
Right, it belongs to someone's phone now, or it's just empty.
So the IT team is forced to literally walk around to 50 different servers and printers, manually typing in IP addresses and subnet masks.
Well, they used to. But network engineering evolved to offer a massive quality of life upgrade. They call it DHCP reservations.
Oh, I see this in the notes.
Yeah.
And the mechanism here is incredibly clever. It bridges the gap between hardware and software.
It really does. So every single piece of networking hardware, whether it's your laptop's Wi-Fi chip or a printer's Ethernet port, has a physical permanent identifier burned into it at the factory.
Right, the MC address.
Exactly, the media access control address. Unlike an IP address, which, changes based on what network you're visiting, your MASI address is fixed hardware.
So instead of physically visiting the printer, the network administrator just goes into the central DHCP server.
Yep.
They find the printer's burned-in MC address, and they just write a rule. They basically tell the server, whenever this specific piece of hardware asks for an IP, ignore the random pool. Always hand it 192.168.150.
That's exactly it. And the real beauty of it is that the printer thinks it's receiving a dynamically assigned temporary address just like any other laptop.
Oh, wow. So it doesn't even know it's a static IP.
Yeah. No. But the DHCP server is essentially rigging the game. It guarantees the permanence of a static IP while allowing the IT team to manage the entire layout from one single server.
So if they ever need to change, say, the DNS server settings for the whole building, they just update it once on the DHCP server, and the printer pulls the new info automatically.
Exactly. It's huge for management.
It's an elegant system, for sure. But relying so heavily on a central DHCP server kind of creates a glaring vulnerability, doesn't it?
It definitely creates a single point of failure.
Right. If you centralize the distribution of all these IP addresses, what happens when that server goes completely offline? I'm picturing an office building where the power flickers, the router reboots, and the DHCP manager just doesn't come back up.
Panic. Usually panic.
Your laptop screams into the void and no one answers. What is the fallback in that scenario?
Well, the fallback is this built-in survival mechanism called APPA, or Automatic Private IP Addressing. You might also hear it referred to as an IPv4 link local address.
APA.
Yeah. When your Windows machine, for example, sends out a DHCP request and hears nothing but silence, it doesn't just give up and disconnect. It actually self-assigns an emergency address from a massive globally reserved block. Specifically, it uses the range of 169.254.0.0 through 169.254.255.255.
Okay, but the notes clarify a technicality there, right? The first 256 and the last 256 addresses in that block are mathematically reserved for system functions.
Right, good catch.
So the actual usable pool your laptop can pick from is 169.254.1.0 through 169.254.254.255.
Exactly.
But wait, if an entire office floor loses the DHCP server, you've got 100 laptops all instantly realizing they're orphaned.
Yep.
And they all dive into that 169.254 pool at the exact same moment.
Yeah.
How do they avoid randomly picking the exact same IP address and causing a massive network collision?
That is the chaotic part. And to solve it, devices rely on something called an ARP Broadcast Address Resolution Protocol.
Okay.
This operates beneath the level of IP addresses down at the physical hardware layer we talked about earlier.
We now see addresses.
Exactly. Let's say your laptop randomly decides to try out 169.254.77.77. Before it actually locks that address in, It uses its physical MSC address to literally shout a broadcast out to the physical switch.
Like it's polling the network.
Yeah, it sends a message to every single connected device asking, hey, is anyone currently using 169.254.77.77?
So it's basically standing in the middle of a crowded room and yelling its new name to see if anyone objects.
Precisely. That's exactly what it is. And if no one replies, the laptop assumes the address is safe and binds it to its network card.
But what if someone does reply?
If another laptop shouts back, hey, I'm already using that, your device simply drops the number, randomly generates a new one, and shouts again.
Wow, that's a brilliant way to establish order out of chaos without a central manager.
It really is.
But we have to make the reality of this failsafe very clear to the listener. What does APA actually look like to the person sitting at the keyboard?
Oh, we've all seen it.
Right. It usually looks like that infamous little yellow exclamation triangle over your Wi-Fi icon in Windows.
Right. That's exactly what it is, because here is the critical limitation of APA. It allows your computer to talk to other computers on your immediate local switch.
So I can still share files with a coworker sitting next to me.
Yes, but an APA address does not provide a default gateway.
Which means no post office, no route out of the neighborhood.
Right. You have zero internet connectivity. If you ever open your command prompt to troubleshoot a dead internet connection and you see an IP address starting with 169.254, you instantly know the root cause.
You know exactly what's broken.
Exactly. The problem isn't your laptop, and the problem isn't your internet service provider. The problem is that your local DHCP server is unreachable. It shifts your troubleshooting focus immediately.
Okay, so APA is a brilliant Band-Aid for a localized temporary failure. But as we move deeper into the CompTIA curriculum, we hit a failure of catastrophic global proportions.
The big one.
Yeah. Let's look at the math of the original IPv4 design.
Yeah.
We have a 32-bit architecture, which, if you calculate every possible combination of those ones and zeros, yields roughly 4.29 billion unique addresses.
Which, when the architects of the internet laid this groundwork decades ago, 4.29 billion sounded like an effectively infinite number.
Of course it did. Who could imagine needing more? But today we have smartwatches, smart refrigerators, tablets, servers. There are well over 20 billion devices trying to connect to a system that structurally only has room for 4 billion.
It's just a math problem.
Right. It's a mathematical impossibility. The internet should have completely run out of room and collapsed years ago.
If we connect this to the bigger picture, the internet did run out of room.
Wait, really?
Oh, absolutely. We technically exhausted the pool of public IPv4 addresses a long time ago, but the network engineers saw the cliff approaching and invented one of the most ingenious hacks in the history of computing to keep the whole thing running.
Okay, I love a good engineering hack. What did they do?
They combined two concepts: private IP addresses, which are defined by a standard called RFC 1918, and network address translation, or NAT.
RFC 1918. It stands for Request for Comment, which is just the agonizingly dry way the Internet Engineering Task Force names its standard documents.
It sounds so boring.
It does. But the mechanism inside that document literally changed the world. It essentially carved out 3 massive chunks of IPv4 addresses and declared them strictly private.
It created a rule that these specific addresses are fundamentally not allowed on the public internet.
Like they're banned.
Pretty much.
Yeah.
If a major internet backbone router sees one of these private addresses trying to cross its path, it will immediately drop the traffic.
Wow.
Yeah. The 3 private ranges cover different scales. The 10.x range offers over 16 million addresses, which is why you see it used inside massive corporate headquarters.
Why do you need the space?
Then the 172.16.x range offers about 1 million addresses. And finally, you have the 192.168.x range,
Which provides around 65,000 addresses. And if you checked your home Wi-Fi right now, there's a 99% chance your phone has a 192.168 address.
Exactly. Because these addresses cannot touch the public internet, they're considered non-routable. And because they are non-routable, millions of different households and businesses can recycle and use the exact same addresses simultaneously.
So your laptop is using 192.168.1.15, and my laptop across town is using 192.168.1.15, and they never conflict because our local networks are completely isolated.
Yes. They never see each other.
Here's where it gets really interesting. If my laptop has a private IP address that is explicitly banned from traveling across the public internet, how on earth am I streaming a movie right now?
Right.
How does my data reach a server in California and come back to me? This is where NAT, Network Address Translation, steps in and performs absolute magic at the router level.
NAT is the unsung workhorse of the modern digital age. Inside your house, you might have 50 devices running on those private, recycled IP addresses. But on the outside of your router, the interface that actually connects to your internet provider, your router, has just one single, globally unique public IPv4 address.
So the router is acting like a proxy.
Exactly.
But I want to explore the mechanics of how it actually keeps track of everything, because it's not just swapping numbers randomly.
Huh.
Let's say my internal laptop sends a request to load a news website. It hits the router. What does the router physically do to that packet of data?
It acts exactly like a highly organized bouncer at a club. Your laptop comes to the door with its private ID, say 192.168.1.15.
Okay.
The bouncer says, you can't go out to the public internet with that private ID. I'll go fetch the data for you. So the router strips your private IP off the request and slaps its own public IP onto it.
So the website only sees the router.
Exactly. But to remember who asked for what, it assigns a specific port number to the request. Think of it like handing your laptop a numbered club wristband.
So it basically writes down in a ledger, wristband number 5001 belongs to the laptop at 192.168.1.15.
Precisely. That ledger is called the NAT table.
Okay.
The router goes out to the public internet using its one public face, grabs the web page data, and when that data comes back, the server sends it to the router on port 50,001.
And the router just checks the ledger.
Yep. It checks the ledger, sees the wristband number, strips off its public IP, puts your private IP back on, and hands the data to your laptop. The external website has absolutely no idea your laptop even exists. It thinks it just had a conversation with your router.
It's an incredible piece of sleight of hand. By using NAT, we can hide billions of private devices behind just a few million public IPs. It literally saves the internet from collapsing under its own weight.
It was a lifesaver.
But at the end of the day, NAT is a Band-Aid. It adds processing overhead to routers. It complicates peer-to-peer connections for things like gaming. And, it doesn't solve the core mathematical limit. We had to build a permanent architectural fix.
Which brings us to the final massive leap in the CompTIA notes, IPv6.
Finally.
The engineers looked at the 32-bit limit of IPv4 and basically decided to completely obliterate the concept of scarcity. They built a 128-bit address structure.
The scale of that jump is so vast that the human brain really struggles to comprehend it. We were going from 4.29 billion addresses to 340 undecillion addresses.
That's 340 followed by 36 zeros.
It's insane.
It is. To put the sheer physics of that number into perspective, you could assign billions of unique public IP addresses to every single square inch of the Earth's surface, and you still wouldn't put a dent in the IPv6 supply.
But to handle that massive string of data, the visual format of the address had to completely change, right? We throw out the 4 octets separated by periods.
Yeah.
IPv6 relies on hexadecimal formatting separated by colons.
Right. Hexadecimal is base 16. Instead of just using numbers 0 through 9, hexadecimal uses 0 through 9 and the letters A through F.
Okay, so bringing letters into the math.
Yeah. This allows a single character to represent a much larger binary value, compressing the massive 128-bit string into something somewhat manageable. You end up with addresses that look like FF80.00000000.00000.5D1 then .0652.cfd.8f52.
Good grief.
Yeah, it groups 16 bits together in these blocks.
It's incredibly visually intimidating, but the notes point out that this massive size actually simplifies network engineering on the back end. Take subnetting, for example. In IPv4, calculating subnet boundaries requires complex binary math just to conserve addresses.
Because every address counts.
Exactly. But in IPv6, because space is effectively infinite, you don't have to conserve anything.
The math becomes incredibly clean. We typically just split the 128 bits right down the middle, creating a 64 subnet mask.
Oh, in half.
Yep. The first 64 bits act as the network prefix, so the neighborhood, and the last 64 bits are the specific host ID, your house. It's a standardized split that makes routing tables hyper-efficient.
But the trade-off is human readability. I can easily memorize that my IPv4 home router is 192.168.1.1. I am never going to memorize a 128-bit hexadecimal string to check my router settings.
No human is doing that.
Right. So in an IPv6 world, automation isn't just a convenience, it's mandatory. Systems like DNS, translating readable domain names into these massive strings, become the absolute lifeblood of the network. Without DNS, navigating an IPv6 internet is impossible for a human being.
It really represents a total surrender to automated infrastructure, relying heavily on systems like DHCPv6 and automated router discovery to handle the incredibly complex math behind the scenes.
So what does this all mean? We started by unpacking the rigid 32-bit structure of IPv4, seeing how devices use subnet masks and default gateways just to figure out where they are.
Right.
We watched IT administrators tame the chaos of corporate networks with DHCP MAC reservations, and we looked at the brilliant, noisy mechanism of an ARP broadcast when APPA has to save a disconnected device.
Shouting in the room.
Exactly. We dissected the sleight of hand of NAT in RFC 1918, cheating mathematical limits.
Mm.
And finally, we looked at the massive 128-bit hexadecimal universe of IPv6.
When you lay it all out like that, you really see the decades of layered engineering, the patches, and the sweeping architectural overhauls that happen in the split second it takes your phone to join a network.
You really do.
Yeah.
But reviewing all this source material leaves me with one highly provocative thought.
Okay, let's hear it.
NAT was invented purely as a mathematical hack to save IP addresses, right?
Yep, just to buy us time.
But as a side effect, it accidentally became one of the greatest privacy tools we've ever had. It effectively hid all of our internal home devices behind that single public router face.
That's very true.
External hackers couldn't easily scan your smart TV or your Wi-Fi light bulbs because they were hidden behind the NAT table.
It acts as a de facto hardware firewall. It rejects unsolicited incoming traffic because, well, there is no entry in the bouncer's ledger for it.
Exactly. But with the infinite space of IPv6, NAT is completely unnecessary. There is no need for private addresses.
None at all.
In a pure IPv6 world, every single device in your house, your laptop, your thermostat, your baby monitor, can have its very own globally unique, directly routable public IP address.
Oh, wow.
So here is the question for you to consider. What happens to the privacy and security of our personal home networks when the accidental hiding place of NAT is finally stripped away and every vulnerable smart device we own is standing naked and directly reachable on the global internet?
That is, it fundamentally breaks the current model of consumer security. We are going to have to rely on sophisticated, proactive firewall rules on home routers rather than just hiding behind a mathematical glitch.
It's a massive paradigm shift.
That's
And it's definitely something to mull over the next time you connect to the Wi-Fi and that invisible handshake begins.
Absolutely.
Well, thank you all for coming along on this journey into the visible architecture of the web. We warmly invite you to join us on our next deep dive.